Hello everyone and welcome to Control Engineering and Control Theory tutorials. In these tutorials we present real and applicable knowledge of control engineering, machine learning, optimization, mechatronics and robotics. This video tutorial is dedicated to the matrix exponential and its application in control theory and control engineering. First, we will show that the matrix exponential naturally appears in the problem of solving a state equation of a dynamical system. Then, we will formally define the matrix exponential, and finally, we will explain how to compute the matrix exponential by using an inverse Laplace transform. This is the first tutorial on matrix exponential, and there will be the second part. In the second part, we will derive several important properties of the matrix exponential, and we will present alternative methods for computing the matrix exponential. A link to the second part is provided in the description below this video. But before I start with the explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 300 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, let's start. First, we need to start with the origin of the matrix exponential. I will show that the matrix exponential naturally appears in the problem of solving a state equation of a dynamical system. That is, it appears in the problem of simulating state trajectories of a dynamical system. Origin. Let us consider a linear dynamical system in the state space form. Here, x is an n-dimensional state vector, x dot is the first derivative of x, and A is a system matrix, n by n. Let us assume that someone gives us an initial condition, x0, that is, x of 0, and that person gives us the following problem. Compute the state trajectory of this system. Okay, to compute the state trajectories, we need to solve this system of equations. So how to do that? Well, we can use the Laplace transform to solve this system of equations. So let's apply the Laplace transform to both left-hand side and right-hand side of this equation. Let's do that. This is how I like to write Laplace transform. I'm applying Laplace transform to the left-hand side, and I'm also applying the Laplace transform to the right-hand side of my system. What is the Laplace transform of the first derivative of x? The Laplace transform is s x of s minus x0. That is minus our initial condition. And on the right-hand side, we need to apply the following law. We know that the Laplace transform is a linear operator. Consequently, Laplace of a times x is simply a, Laplace of x, and Laplace of x is x of s. Let's rearrange this equation. From this equation, we obtain s x of s minus a x of s is equal to x0. Okay, now, since x is a vector, we can write the left-hand side like this. Times x of s is x0. From this equation, we can express x of s as inverse of s times the identity matrix minus a times x0. Here, to repeat, I is the identity matrix. To make this video tutorial as clear as possible, I erased the previous part and I repeated my equation over here. Okay, this matrix over here has a special name. I will write it again over here, and I will write its name. This matrix is called resolvent matrix of A. To repeat, the matrix S times I minus A inverted is called the resolvent matrix of matrix A. Our main goal is to compute x of time from this equation. To compute the x of time, that is, to compute our state trajectory, we need to apply the inverse Laplace transformation to this equation. Consequently, we will type x of time is the inverse Laplace transform of x of s, and x of t is then equal to inverse Laplace transform of the right-hand side. Here's our resolvent matrix, and here's our initial condition vector. Since the inverse Laplace transform is a linear operator, we have the following expression. This matrix over here has a special name in control engineering and control theory. This matrix is called the state transition matrix, and usually it's denoted by the capital letter phi, the Greek capital letter phi, of time, and over here I will write the complete expression, inverse Laplace transform of the resolvent matrix. And I will write the name. The matrix is called state transition matrix. By using this definition, we can write our x of time as a multiplication of our state transition matrix and our initial condition vector. And now, from this equation, you can see the main reason why this matrix is called the state transition matrix. It helps us to map the initial condition to the state in the future. We simply take the initial condition, x0, we multiply this initial condition by our state transition matrix, and we obtain the state at any time instant x of t. Now, the main challenge is how to compute this state transition matrix. Obviously, we can compute Si minus A, and we can invert. Right, we will have an expression that depends on the Laplace transform. And then, this is a matrix actually, and after that, we can compute an inverse Laplace transform of that matrix. To compute an inverse Laplace transform of a matrix, we simply take an inverse Laplace transform of every entry of this matrix and we form the matrix at the end. That's not a big deal. In the sequel, I will show you that the state transition matrix is actually equal to the matrix exponential. Here it is, the matrix exponential of A times time. And this is the fundamental formula in control engineering and control theory. The state transition matrix can be expressed as the matrix exponential of A times time. The matrix exponential is defined by the following expression. Is equal to identity matrix plus A times t plus A squared t squared divided by 2 factorial plus a to the power 3 multiplying t to the power 3 divided by 3 factorial plus a to the power 4 multiplying t to the power 4 divided by 4 factorial and plus higher order term that are determined on the basis of the general pattern. So what is the general pattern? We can write our matrix exponential in the compressed form as the following sum. Sum where the index I goes from 0 to infinity. Then we have inside, you can stop here for a second and think, what is the general expression over here? It's very easy. It is a to the power I multiplying t to the power I divided by I factorial. Here, t is time. And if you forgot, I factorial is defined as I times I minus 1, I minus 2, until 1. This seems like a very complex expression. However, maybe it's not so complex. Let me ask you the following question. Does this expression remind you of something that you learned in basic calculus? Think about it. Obviously, this matrix expression is a generalization of the Taylor series expansion of the scalar function. Do you remember the Taylor series expansion, or better to say Maclaurin series expansion of e to the power at, where a is a scalar? The Taylor series expansion, or better to say the Maclaurin series expansion, is 1 plus at plus a to the power 2 t squared divided by 2 factorial plus a to the power 3 t to the power 3 divided by 3 factorial plus a to the power 4 t to the power 4 divided by 4 factorials, and etc. And you can see the analogy. If we take the classical Taylor series expansion of our exponential function, and if we substitute scalar a by a matrix, let's say capital A, capital A, capital A, capital A, capital A, etc., we will exactly obtain this expression over here. However, we still didn't answer the main question. And the main question is the following one. What motivates us to define the matrix exponential like this? Well, the motivation for introducing this definition and this particular form of the right-hand side follows from the fact that if we expand our resolvent matrix into a series, that is, into a matrix series, and if we compute the inverse Laplace transform of our resolvent matrix, we will exactly obtain this term on the right-hand side. And that's precisely our matrix exponential. And that's the motivation. So let's show that. Previously, we have shown that x of t can be expressed as the state transition matrix times x0. And we claim that the state transition matrix is actually our matrix exponential, and that's precisely the inverse Laplace transform of our resolvent matrix. In the sequel, I will show that this inverse Laplace transform is actually equal to the following expression: identity plus at plus a squared t squared divided by 2 factorial plus a to the power 3 multiplying t to the power 3 divided by 3 factorial plus a to the power 4 multiplying t to the power 4 divided by 4 factorial, etc. That is, we will show that by computing the inverse Laplace transform of our resolvent matrix, we will actually obtain the matrix exponential. The first step is to expand our resolvent matrix into series expansion. That is, we want to write this matrix as a sum of terms involving a squared, etc. How to do that? Well, to do that, we have to remember one formula from matrix analysis. Let Q be an arbitrary matrix, and let us try to expand this expression. Under some mild condition and assumptions that I will not state here in order not to make this video tutorial too complex, we can expand this expression as follows. Identity plus q squared plus q to the power 3, etc. Let's apply this formula to this equation. To apply this formula, we first need to get rid of this s. That's easy. We can simply write si minus a inverse as s multiplying identity minus a over s inverse. We have 1 over s multiplying identity minus a over s inverse. Consequently, we just apply this formula to this expression under the assumption that q is a over s. So let's do that and let's see the result. We can write 1 over s multiplying I minus a over s inverse is equal to 1 over s multiplying the following expression inside. Let's see what do we have here. We have identity plus a over s plus a squared over s squared plus a to the power 3 over s to the power 3 plus a to the power 4 over s to the power 4, and we have higher order terms over here. Then, if we multiply 1 over s with these expressions, we obtain 1 over s identity plus a over s squared plus a to the power 2 over s to the power 3 plus a to the power 3 over s to the power 4 plus a to the power 4 over s to the power 5 plus higher order terms. To summarize, we expressed our resolvent matrix as a matrix series shown on the right hand side. The state transition matrix is defined as the inverse Laplace transform of our resolvent matrix. Let us apply the inverse Laplace transform to this right hand side. To apply the inverse Laplace transform, we have to recall a few properties of inverse Laplace transform. What is the inverse Laplace transform of 1 over s? It's obviously 1 times Heaviside function, however, I will just write 1 over here. What is the inverse Laplace transform of 1 over s squared? The inverse Laplace transform is obviously t. What is the inverse Laplace transform of 1 over s to the power 3? How to do that? Well, 1 over s3 is 1 over s multiplying 1 over s squared. That's the integral of this term over here. And the integral of t is obviously t squared divided by 2. What is the inverse Laplace transform of 1 over s to the power 4? The inverse Laplace transform of 1 over s to the power 4 is 1 over s multiplying 1 over s to the power 3 That's the integral of this expression, and the integral of this expression is t to the power 3 over 3 times 2. Now, in the general case, what is the inverse Laplace transform of 1 over s to the power n? Obviously, the inverse Laplace transform of 1 over s to the power n is t to the power n minus 1 divided by n minus 1 factorial. Let's apply these rules to our original expression, and let's see what do we get. Our state transition matrix is, what's the Laplace transform, or better to say inverse Laplace transform of this term? The inverse Laplace transform of 1 over s is simply 1. Consequently, I will write here identity matrix. What's the inverse Laplace transform of a over s squared? To solve this inverse Laplace transform, we need this expression. Consequently, we will write a times t. What's the inverse Laplace transform of this term? We need to apply this formula. We have a squared multiplying t squared divided by 2 factorial. The inverse Laplace transform of this term is a to the power 3 multiplying t to the power 3 divided by 3 factorial, and the inverse Laplace transform of this term is a to the power 4 multiplying t to the power 4 divided by 4 factorial, and plus higher order term that repeat in the same pattern. Now, does this expression look familiar to you? Yes, it looks familiar. This is exactly our matrix exponential. Consequently, we have shown that state transition matrix, that is the inverse Laplace transform of our resolvent matrix, is precisely the matrix exponential. And that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.